So let's talk about capacitor circuits. All right, what is a capacitor circuit? Well, it's a circuit that consists of a battery and a bunch of capacitors. Now, we're going to start with these capacitors uncharged. And notice the way that I've written this. I've got a little switch so that current can't flow until I close the switch. All right, as soon as I do that, current is going to flow and start charging up the capacitors. Remember that the purpose, the job of a capacitor is to store charge. So that current flows up into the capacitor and it can't jump across. But what will happen is this guy will start being charged positive, and then that'll scare all the positives away from the other side. So we get negative there. The positives will then go down and charge here and here. And then that'll scare the positives away, so we'll get some charge there. And then we've got all the negatives on the negative side of the battery and all the positives on the positive side. So what's going to happen is there will be current that flows until the potential differences across these capacitors balance the potential difference across the battery, and then no more current will flow. So in a capacitor circuit, current flows until the capacitors are full. They can't eat anymore, so no more current can be forced into them. This is called steady state because there no longer are any changes. All right, now aside from that kind of qualitative understanding, the difference between a capacitor circuit on the one hand and a resistor circuit on the other, aside from that, we solve everything basically the same way. We look at our network and we say, how can I combine these capacitors either in series or in parallel to make it a simple circuit that consists only of a battery and a single effective capacitor? And then what we do is we reconstruct the circuit, the original circuit, just by going back through our analysis. All right, so let's go ahead and do this. The first thing, it's obvious, these two 4 farad capacitors are connected in series. So that means that we have to combine them in series. Remember, in series, capacitors add in reciprocal. Now, this is especially easy when, as in this case, it's the same resistance, because we'll do 1/4 plus 1/4, and that'll give us 2/4. So when we flip it back upside down, it's going to be 4/2. That happens anytime you have two capacitors that have the same capacitance connected in series. The effective capacitance is just 1/2. All right, so we'll write up the circuit as follows. Just like that. This is the series combination of the two 4 farad capacitors, so it gives us 2 farads. Over here we got 8, here was 15, and over here our battery is 10 volts. All right, easy enough. What's next? Well, the 8 and the 2 are clearly connected in parallel. Now the nice thing about parallel with capacitors is that you just add. So we'll have, this is 10 volts, this is 15 farads, and this over here, 10 farads. All right, now these two guys are in series. So let's combine them in series. Again, it's 1/15 plus 1/10. And it turns out that that ends up giving you 1/6. All right? So that means that this circuit really is nothing more than this circuit. 6 farads, 10 volts. All right, now we need to know how much charge is on our effective capacitor. Well, potential difference is Q over C, so Q must be C times potential difference. 6 times 10 gives us 60 coulombs. And now we'll just reconstruct the circuit. I'll show you how to do this and then we'll look at the answers. All right, so in series, charge is the same. So that means that both of these capacitors have 60 coulombs. All right. Now, 60 coulombs with 15 farads, potential difference is Q over C. So this guy is 4 volts. What does that mean this one's supposed to be? Well, he's supposed to be 6 volts because I got 10 altogether, 4 here, so I got 6 left over. Another easy way that we could do that is just Q over C again. 60 over 10 gives 6. All right, so now I've got my 15 all covered. 60 coulombs, 4 volts. So how am I going to reconstruct my 8 and my 2? Well, they combined in parallel. And remember that in parallel, potential difference is the same, right? So that means that the potential difference here across both the 2 and the 8 must be 6 volts. All right, then we do C times V, and that's going to give us the charge. 2 times 6 is 12. 8 times 6 is 48. All right, so that's the way that it goes. Notice, of course, that 48 plus 12 gives us the 60 that was on the 15 farads. After that, we'll break this 2 back into the 2 4s. I'll let you do that one on your own. Let's go ahead and look at the answers. So I'm going to put them in a table just like this. Capacitance in farads, potential difference in volts, charge in coulombs. Now, as before, I've got the 4 guys that I had on the original circuit, but then at the bottom, I've got an effective capacitance, the 6 farad guy. All right, now there is a check, just like there is in resistor circuits, that checks all of our math, just to make sure that we get everything correctly. And that check is by asking how much energy is stored by all of our guys, right? So remember, energy you can get just by doing Q squared over 2C, or 1/2 CV squared, or 1/2 QV. So doing that in each of these cases gives 18 joules of energy by both of the 4 farad capacitors, 144 joules for the 8 farad, and 120 for the 15. All right, now if I add all these up, what I end up with is 300 joules. That's how much energy total is stored in my capacitor circuit once all the capacitors are full. They can't take any more current. So that means that that 300 joules has got to be stored in my effective capacitor. All right, let's go through and do it. The potential difference across the effective capacitor is just that 10 volts that we had across the battery. To get the charge in coulombs, we do capacitance times potential difference. And then to determine the amount of energy stored, we need to do 1/2 CV squared. So 1/2 times 6 is 3 times 10 squared, 300. Since those two numbers agree, it means pretty much that we didn't make any mistakes. And that's capacitor circuits.